Hi, my name is Michael Kagan. I am from NVIDIA, and I'll talk about AI and the storage and how they are related to each other. So today, everything is connected, generates data, and the data processing and its storage becomes more and more interesting. There is a lot of different types of data, data in flight, data in rest, fast data, data that real time need to be correlated with archives. And this actually requires new way of data processing and data access. The AI, artificial intelligence, becomes the dominant data processing paradigm, and it's becomes way of life. And with the more use of AI, more technologies are developed, and more data and faster models and more precise models in several domains. Actually, neural networks exceed human capabilities, like in image recognition and speech recognition. We are now talking about real-time translation, and chatbots become the first line help, and healthcare, everything becomes the AI driven. AI becomes our life, and what it ends up with is that it generates more and more data. We generate more data every year. It's data pretty much doubles every year, the amount of data, and this opens up, actually opened up a couple of decades ago, a new opportunity to create applications or create services which are similar, which are different than one human machine creation, but it's training the neural network models. And this actually took us to a fairly interesting journey, because when 20 years ago we were developing the program, the people were thinking about the algorithm, then sitting in front of a computer and typing the code that would implement this algorithm. And after some debug sessions, the applications were actually created, and it didn't require much compute power to create the application. It was just the word processor. Now, in order to run the application or actually get the service out of the application, there was a very fast computers were deployed. So the mainstream was, you write the application, then you use the mainstream to run CAD tools or dynamic, fluid dynamic simulations or things like that. When you go to the neural network model, the things sort of flipped. In order to create the application, what we are doing, we are running the massive amount of data through the computing to the computer to train the neural network. It takes months to train advanced neural networks on the very fast computers. And once network is trained, it can actually even be pruned. And then in order to, the applications actually, the inference on this neural network, and it can be done, it's actually being done on the much less power computers than it was used to train the data, train the neural networks. Every cell phone or even watch integrates the neural network that was trained in the data center. So this is something that we need to take into consideration, that when we create the application or customize our neural networks, we need much faster computer than we used to run it. So now the data growth and the CPU performance actually gone to the different directions. The data growth was accelerated, but CPU performance with the slowdown of Moore's law, where the amount of transistors that you can put on the single device didn't grow as fast as it used to be before. The performance of the CPU, the growth in the performance in the traditional processor slowed down, because now you need to come up with the new architecture, new solution, because so far the CPU, the von Neumann machine performance were mainly attributed to more and more transistors that were on the disposal of the CPU designers. So in order to satisfy the growing computing needs, the new technology came up, the new architecture came up to take care and to help here. And this is GPU. It is the original graphics technology that was developed for graphic processing, highly parallel machines, vector processors. It is very suitable for neural network type of processing. And actually GPU becomes the general processing unit for artificial intelligence. And in past decade, GPU performance grew by 3 orders of magnitude, about 1000x. So in 10 years, every year GPU performance were pretty much doubling. And the model that it took a month to train 10 years ago now can be trained in less than an hour. So the AI models and AI services started as that people were developing the sort of or in open community were developing the AI models for different tasks like speech recognition or image processing, and or handwriting recognition. And these models were trained in the data centers on the public data that were stored and collected by the service providers. And once the model is trained on the data, it could be deployed on the cell phones or any other gadgets. So once we have the trained model, you can actually customize it by personal data. For example, speech recognition, you can customize the speech recognition for individuals. And actually, once you have these standard models, you can use the custom data to train the model. And this needs to be done in the data center because people cannot afford the compute power required to train the model. And actually it happens today. People also started to develop their own neural network models. And now we need to have to deliver the services to the customers, which are compute services for training the neural network models. And these services can only be delivered in the big data centers, and definitely not everyone can afford the compute power that's required to train the neural network. So the data center becomes a new unit of computing that needs to serve billions of users. And these applications and services in the data center are actually built out of the microservices. So there's a containerized microservices that can shrink and grow based on demand of the billions of users that are using this machine. And it actually also enables the collaboration between people that don't know each other. Like in this example, you show here traffic navigation like Waze. People help each other to outsmart traffic without even knowing each other. So when we go to the data center as the unit of computing, it is based on the 3 pillars, which is CPU is the von Neumann machine traditional CPU that handles the application framework. It is the GPU, which is the main data crunching engine. And it is the DPU, which is the infrastructure computing platform. DPU is the new kid in town. It actually runs the operating system of the data center. And the data center services are based on data. And the data is both coming in the real time, and it comes from storage. and many services are based on accessing the data from the databases. So when you access the data in the database, whether you build applications that are based on microservices, it is not a monolithic application anymore, and the completion of your service depends on the last microservice completed. And therefore, average latency is not necessarily a mean to assess the performance, because average latency latency may hide the outliers. And sometimes the access to the data can be 3 orders of magnitude, or maybe even more than 3 orders of magnitude higher than the average. So average doesn't tell you a lot. It's like, you know, if Bill Gates enters the pub, then all of a sudden the average wealth of pub guests becomes $1 billion. But nobody becomes a billionaire out of it. So it's not very useful. So, and if you have this situation with the outliers, you can have a very unpleasant effect of not being able to deliver predictable performance. So we'll talk about how do we cut the outliers, in particular in the storage applications and the database access applications. One of the challenges in the database access is consistency. And if you have a precise clock distribution within the data center, then you can have a much you can cut significantly the outliers, because the amount of retries that you need the cases that you need to retry reduces significantly. So with the DPU, we are able to synchronize clocks within the data center to the accuracy of tens of nanoseconds, while conventional clock synchronizations is many microseconds or sometimes even milliseconds. This is one of the means to reduce significantly the tail latency and take care of this tailored scale problem. So the data processing becomes a challenge, and it needs to be done in the optimal place. It can be done in the network itself. It can be done in the CPU and the GPU and the DPU, in the switches and the storage devices themselves, storage controllers themselves. And storage access interfaces can be amended, actually is being amended for to reduce the tail latency problem and have more deterministic latencies. And you can do some remote processing, which is close to the storage media itself. So when we talk about storage controllers, we talk about things that are doing computation which is related to the storage. It can be reliability, like mirroring the data. It can be it can have accessing the data in the multiple places to make sure to get the fastest result sooner. It can be for more efficient media management, and there's multiple solutions or multiple products for efficient flash media management. It can be compression, it can be deduplication, and the like. But actually, there is more interesting opportunities there, because when the data is stored, in many cases it's unstructured data. It is data that is coming from the users, and you can prepare the data for subsequent accesses and to enable more to structure the data while it's stored. You can prepare the data. And in these smarter storage devices will execute not just storage related computing like compression and deduplication and the like, but also some data analysis. You can run the object recognition. You can do the tagging. You can do some continuous data mining. So the data will be ready in the storage device itself for the application access. So additional challenge is to have the software and hardware interfaces so the data is moved efficiently and directly to the compute element without intermediate storage and the intermediate stations. It's a faster way to connect to memory. It is having the persistent memory semantics over the network. It is the faster PCI Express. It is extending coherency beyond CPU domain. It is extending the memory access semantics beyond just the memory interface. And you can package multiple elements together. It can be the computing, it can be a GPU, it can be memory, it can be flash. It's all in one package. So there is in-network computing is yet another mean to make a more efficient and more predictable execution. First of all, of course, the faster network is required to keep up with the faster storage media. The acceleration of the infrastructure, and actually in our DPUs in the NVIDIA, we put the AI accelerators in the DPU itself, and now we can have the AI acceleration not only for the application processing but also for the infrastructure itself. You can do better security based on the data processing, processing the data and correlating the archived data with the archived behavior and the traffic patterns with the current one, and detect anomalies by processing much more data than you could before. You have a faster network performance in the computing itself. And last but not least, time synchronization enables to cut off the tail latency effect for the database accesses. So to summarize, the artificial intelligence paradigm, it is data processing is basically becomes dominant data processing paradigm. It is everywhere. It requires more and more data, and there are different types of data, and we need to have a data to process the data in the right place and prepare the data for processing. It is you need to have a new data center that is basically distributed computing platform that serves billions of users. And talked about tail latency, and you need to have a processing of the data in the right place, and sometimes it needs to be close to the media itself. Sometimes it needs to be in flight, and you need to have a much more efficient and optimized interfaces between the computing and the storage and data itself. So this concludes my talk. Thank you very much for your attention.